Selam Liam in for bear. A user types a question into a product, and LLM answers. Between those two events, 6 layers, at least 18 services, and a set of trust boundaries that most teams draw in the wrong places. We are going to map all of it. Why does the architecture matter? Because the attack surface is the architecture. Every service a request touches is a place it can be manipulated, poisoned, or intercepted. A production AI system is not a model, it is a pipeline, and the security decisions made at design time determine what is possible at incident time. Layer 1, the edge. Before any request reaches application code, it passes through a CDN and DNS, hits a load balancer, crosses an API gateway, gets authenticated and rate limited, and passes through a web application firewall, standard infrastructure. The WAF is configured for known web attack patterns, SQL injection, cross-site scripting. It knows nothing yet about prompt injection. Layer 2, the application layer. A workflow engine coordinates multi-step requests. A RAG service manages retrieval augmented generation. Prompt builder assembles the final input to the model. An agent orchestrator coordinates agents when needed. Also in this layer, user management, tool execution, evaluation, billing. This is the most complex layer and the one that matters most for AI-specific security. Layer 3, the model tier. Foundation models are the obvious center. Also here, embedding models that convert text to vectors, re-ranker models that reorder retrieved chunks before the prompt, and guardrail models that filter inputs and outputs. Light LLM and Open Router both act as model routing proxies. Light LLM self-hosted, Open Router managed cloud, normalizing dozens of providers behind a single API. Vendor lists here are illustrative. Not endorsements and not complete. Layer 4, knowledge and data. Vector databases hold the semantic index. Knowledge graphs hold structured relationships. SQL databases hold transactional records. Object storage holds large files. A search index and cache round out the layer. The contents of these stores are what the model reasons over. Whatever goes in, the model will eventually repeat. That makes the knowledge layer a persistent target. Layer 5, ingestion. Data enters from connectors, databases, APIs, document repositories. Parsers extract structure from raw files. Dockling from IBM Research and unstructured.io both handle heterogeneous formats, PDF, Word documents, HTML, converting them to structured text for LLM consumption. Transformation pipelines clean and route. A note on dbt, it lives here only if data is already loaded into a warehouse. It is a transformation tool, not an extract and load tool. Streaming systems handle real-time updates. Layer 6, infrastructure, compute containers, serverless, CI/CD pipelines, identity and access management, monitoring and logging. Langsmith belongs here. It is an observability and tracing tool for LLM runs, framework agnostic, built by the LangChain team, not a model or a guardrail. These systems run everything else, and they see everything that passes through. Now watch one request travel. A question arrives at the edge, authenticated, rate checked, WAF inspected. The workflow engine routes it. The RAG service queries the vector store, retrieved chunks return. The prompt builder assembles them with the system prompt in the user query. The guardrail model checks it. The foundation model generates an answer. Evaluation scores it. Billing records the token cost. The answer reverses the path. That is the happy path. The architecture tells you what can go wrong before your attacker does. Now the security argument. Standard architecture diagrams in this space place a security layer at the bottom, beneath infrastructure. That is the perimeter model, one gate at the base, everything inside is trusted. In a traditional web application, that is a reasonable simplification. In an AI system that retrieves external content and executes tools on behalf of a user, it is not. The distinctive attack surface in an AI system is in the middle of the stack, not at the perimeter or the basement. Prompt injection enters not through the user field, where you are probably already filtering, but through the RAG path. Index poisoning happens not at the WAF but at ingestion. Model output lands in downstream sinks that need the same skepticism as user input. The security boundary needs to distribute one decision at every hop that touches untrusted content. OWASP Top 10 for LLM Applications 2025 lists LLM 01 2025 prompt injection as its first entry. The RAG path is the most underappreciated injection vector. A document in your knowledge base can contain text that instructs the model to ignore previous context. When the retrieval system pulls that chunk and the prompt builder inserts it without sanitization, the model reads it as instruction. Retrieved content is untrusted input. Treat it exactly like user input because an attacker can arrange for it to be. Tool execution is where an agent takes its most consequential actions, calling APIs, running code, reading files, writing to databases. The agent is privileged. If the LLM driving it has been manipulated via prompt injection, it can be made to abuse those privileges. This is the confused deputy problem. A privileged component is tricked by a less privileged one into misusing its access. The blast radius is exactly what the tool is permitted to do. Scope tool permissions to the minimum required for the task. The knowledge layer is a persistent attack surface. If an attacker can influence what gets indexed by injecting a document through a public channel your connector reads, by poisoning a data source that feeds your ETL pipeline, every future retrieval that touches that content is affected. This is not a runtime attack. It is a supply chain attack on your data. Validate and sanitize at ingestion. Audit what gets indexed. Treat the index as having the same trust level as the application that reads from it. The model's output is a string. It goes somewhere: SQL query builder, a code executor, a browser renderer, another agent in a multi-agent pipeline. Each of those downstream syncs must treat model output with the same skepticism you would apply to user input. An LLM that generates a SQL clause can be made to generate a destructive one. One that generates HTML can be made to generate a script injection. Output sanitization belongs between the model and every downstream sync that acts on the string. 3 practices that apply at every hop. First, redact before logging, not after. PII and secrets that pass through the prompt must not end up in your observability stack in plain text. Redact at the hop before the telemetry write. Second, authorize per action, not just at the edge. A token at the API gateway does not prove the agent should call this specific tool for this specific user. Validate at each trust boundary. Third, keep secrets out of prompts entirely. If your prompt builder is assembling API keys into context, that is your next audit target. The trade-off is worth naming explicitly. Every guardrail costs latency and adds a failure mode. A guardrail model that errors needs a fallback policy. Redaction at every layer adds compute. Per hop authorization adds round trips. Security by layer count is not a design. Stacking guardrails without knowing what each one covers just moves the gaps. The goal is coverage at the right trust boundaries with explicit behavior when a check fails. Name the trade-offs. Measure the latency. Make the policy decisions explicit. The architecture of a production AI system is a trust boundary map. The edge handles volume and known web attacks, not prompt injection. The application layer orchestrates and is where injection enters via the RAG path. The model tier routes and guards. Guardrails are a gate, not a guarantee. The knowledge layer persists what the model reasons over, including what an attacker seeded at ingestion. Security is not a slab at the bottom. It is a decision at every hop. Your turn, take this into a Claude session. Paste a simplified diagram of your own system, even a rough sketch in text, and ask Claude to label every hop where external or retrieved content enters the prompt. For each hop, is this content trusted or untrusted? What can the component downstream do? What is the current sanitization policy? Flag any hop where untrusted content meets a privileged downstream action. That is where your trust boundary actually is. I'm Liam, in for Bear.